Ever clicked on a website, maybe during a big sale or something, and
Yeah.
just nothing, just that spinning wheel?
Oh, yeah. Or just crawls.
Exactly.
Yeah.
It really makes you wonder, uh, how do these massive online services handle literally millions of us clicking and browsing, all at once without the whole thing just grinding to a halt?
It's a huge technical challenge, definitely. And the solutions they use are, well, they're pretty much essential for the internet we use every day.
Totally. And that's what we're diving into today, this world of load balancing algorithms. These are like the unsung heroes, the secret sauce, making sure things run smoothly behind the scenes, especially when traffic gets crazy.
The traffic cops of the internet, maybe.
Yeah, good one. So our mission here is to really get our heads around the main ideas behind these different methods. And importantly, why choosing the right one is so critical if you're building, scalable systems. We're working from a document here that outlines some key algorithms.
Sounds good.
Okay, so let's start at the beginning. What is a load balancer, fundamentally?
Right. So basically, a load balancer acts as a sort of traffic director. When you send a request, like clicking a link on a website, it doesn't usually go to just one single server waiting for it.
Okay.
Instead, it hits the load balancer first. And the load balancer's job is to look at a group or pool of servers and decide which one should handle your request. It distributes the incoming traffic.
Ah, okay. So it spreads the load, stops any one server from getting totally overwhelmed. Makes sense.
Exactly. Keeps things running faster and more reliably.
Got it. Now, this document we have lists 7 essential algorithms. Let's jump into the first one, round robin. Sounds circular.
Yeah. Yeah, it pretty much is. Round robin is like the most basic. It just hands out requests to the servers one after the other in a simple loop.
So request 1 goes to server A, 2 goes to B, 3 to C, and then the next one loops back around to A again.
Precisely. Like dealing cards from a deck, one for each player in turn. It's straightforward, and it works pretty well if, and this is a key if, all your servers are roughly equal in power and the requests are all kind of similar.
Okay, but what if they're not equal? Like, if server B is way older or slower than A and C, wouldn't it get swamped eventually, even getting the same number of requests?
That's the potential downside, yeah.
No.
Simple fairness doesn't always mean equal distribution of work if the workers aren't identical. Which leads nicely into the next one, actually.
Which is sticky round robin. Okay, so round robin, but sticky. What does that mean?
It means it adds something called session persistence or stickiness. It still uses the round robin idea to initially assign you to a server.
Uh-huh.
But then for the rest of your session, basically, while you're actively using the site, it tries to keep sending all your subsequent requests back to that same server.
Ah, I see. So if I log in, it tries to keep me talking to the same machine. Why is that useful?
Well, think about something like an online shopping cart.
Okay.
Often, the details of what's in your cart might be stored temporarily on the specific server you're connected to. If your next click sent you to a different server.
My cart might suddenly be empty.
Exactly. Or you might get logged out or lose some other context. Stickiness maintains that consistency for your session. It makes the user experience much smoother in those cases.
Right. Okay, that makes a lot of practical sense. So, moving on. Weighted round robin. This sounds like it directly tackles that issue we raised about servers having different capabilities.
It does. With weighted round robin, you don't treat all servers equally. You assign a weight to each server, usually based on its capacity, like its processing power, memory, that sort of thing.
So my shiny new powerful server gets a higher weight.
Right. And a server with a higher weight gets a proportionally larger slice of the incoming traffic compared to one with a lower weight.
So if server A has weight 3 and server B has weight 1, server A would handle roughly 3 times as many requests as B in the rotation.
Something like that, yeah. The exact mechanism can vary, but that's the core idea. It lets you leverage your more powerful hardware more effectively. Useful if you've got, say, a mix of old and new machines.
Makes sense. You want your best players getting the ball more often.
Precisely. Though figuring out the right weights can sometimes be tricky. Do you set them statically or try to adjust them based on real-time performance? That's a whole other layer.
Good point. Okay, next algorithm. IPURL hash. This sounds a bit more technical. Hash.
Yeah, it's a different tactic.
Yes.
Instead of just rotating, it uses a mathematical function, a hash function. It takes some piece of information from the incoming request, usually either the user's IP address or maybe the specific URL they're asking for,
Oh, okay.
and it feeds that into the hash function. The output of that function, the hash value, then determines which server gets the request.
Okay, so what's the result of doing it that way? Why use a hash?
The key thing about a good hash function is that the same input will always produce the same output.
Right.
So if you base the hash on the user's IP address, all requests from that same IP will consistently get hashed to the same server. Or if you hash the URL, all requests for that specific page might go to the same server.
Ah, so it achieves a kind of stickiness again, but in a different way. Like, my computer always gets sent to the same server, or requests for the homepage always go to a specific server.
Exactly. It provides user affinity or server affinity. The advantage can be better cache utilization. If one server has already fetched and stored a copy of a popular page, cached it, sending subsequent requests for that same page to that server is much faster.
Gotcha. So it can be more efficient for certain types of content. Interesting. Okay, number 5, least connections. The name seems pretty descriptive.
It is. This one's more dynamic, more aware of the current state of the servers. The load balancer actively keeps track of how many active connections each server is currently handling.
Okay, so it's counting ongoing tasks.
Essentially, yes. And when a new request comes in, the load balancer simply sends it to the server that currently has the fewest active connections.
That sounds pretty smart, like joining the shortest queue at the supermarket.
Exactly like that. It's trying to find the server that's likely least busy right now. This is really good for situations where the workload per connection can vary a lot, or connections last a long time.
So if one server got hit with a few really complex, long-running database queries, even if it hasn't had many new connections recently, the load balancer would see it's still busy and send new quick requests elsewhere.
That's the idea. It adapts to the current load rather than just following a fixed pattern. It helps prevent one server getting bogged down while others sit relatively idle.
Right, so we're seeing a progression here, from simple rotation to methods that consider server power, user sessions, and now real-time load. What's the trade-off, though? Is least connections more complex to implement?
Generally, yeah, it requires the load balancer to maintain more state information about the servers, which adds a bit of overhead. But the potential performance gain in the right scenarios often makes it worthwhile.
Okay, last one on our list, geoload balancer. This one feels intuitive, based on geography.
Precisely. Geoload balancing routes users based on where they are in the world. The main aim is to connect users to the data center or server that's geographically closest to them.
So if I'm logging in from London, I get sent to a European server, not one in, say, California.
Ideally, yes. Or at least to the closest available point of presence. The shorter the physical distance the data needs to travel.
The faster things load, lower latency.
Exactly. Reduces lag, speeds up response times. For any big global service streaming sites, social media, CDNs, this is absolutely essential for providing a good user experience everywhere.
Makes total sense. You really feel that difference when you hit a site hosted far away. Okay, wow. So that's 7 different strategies. Round robin, sticky round robin, weighted round robin, IP URL hash, least connections, and geoload balancer.
Quite the toolkit.
It really drives home the point that there isn't just one best way to do load balancing, is there?
Absolutely not. And that's a key point in the source material we looked at. It said something like, your load balancer is only as smart as the algorithm behind it.
Yeah, I remember that line. The intelligence is in the strategy you choose.
Right. The algorithm dictates how effectively you distribute that traffic, how well you handle different kinds of loads, and ultimately how good the experience feels for the end user.
So the big takeaway seems to be, you've really got to understand your application's specific needs, know your server capabilities, and think about your traffic patterns to pick the right load balancing algorithm.
Couldn't have said it better myself. It's about matching the tool to the job. Understanding these different approaches is, well, pretty fundamental for designing systems that can actually scale up and stay reliable.
Okay, so here's something for you, the listener, to chew on. Think about the apps and websites you use all the time. Based on what we've just talked about, can you guess what kind of load balancing might be happening behind the scenes? When would simple round robin maybe be enough? When would you absolutely need something like sticky sessions maybe for your online banking? Or where have you really noticed the speed benefits that probably come from geoload balance?
Yeah, thinking about those real-world applications really helps solidify the concepts.
It does. It gives you a whole new perspective on the hidden complexity that makes the internet work as smoothly as it usually does.
Hopefully this deep dive has given you a good starting point for appreciating that. It's a really fascinating area, the infrastructure that holds everything together.